We're live. Welcome to what you should learn, and this is rational functions. And a rational function is called a rational function not because it's not crazy. It's called a rational function because it's made up of ratios. Okay, that's why it's called a rational function. And a rational function is a function like where you have one polynomial divided by another polynomial. So it's like something like 3x squared over 2x minus 5. That's an example of a rational function when you have one of those over there. And rational functions are different than polynomial functions. Polynomial functions, they're smooth. Remember, they kind of go up and down, and there's no breaks in them. Rational functions have things like holes in the graph and asymptotes. Asymptotes are things that graphs approach but never touch. So you could have rational functions tend to look like this, but there's many, many different varieties of rational functions. Okay? And we're going to learn about some real life problems, Greg.
Yes,
at the end,
my favorite.
using rational functions. Okay? So, so anyway, introduction to rational functions. There you go. You don't write everything down. So a rational function can be defined as, I need to remember to put my pen on this. A rational function can be written in the form nx over d of x, in which this is a polynomial and this is a polynomial. So in the last case, I gave an example of, I don't know if this was the example, 3x squared over 2x minus 5. That's an example. That was it?
Yeah,
right on.
Okay. So that's an example of a rational function. Okay? Where n of x and d of x are polynomials, and d of x is not the zero polynomial. So you can't have 0 down here. And we'll talk about the domain in a second, so don't worry about all that verbiage there. And just so you know, tomorrow I'm going to give you a handout that has a lot of the rules, because today we're going to talk about how you find asymptotes and how you find holes in the graph and things like that. And I'll give you a big sheet, so you don't have to write down everything that you see here. But this is a good one. Find the domain of f of x, and to discuss the behavior of f near the excluded value of x. So anyone know what f of x equals 1 over x looks like? You might have seen it. I bet you saw this last year. Did you not see this? Anyone know the shape of it? What does it look like? Well, yeah, it's just like what I did before. Good. They teach that in France. Yes? Yeah. Maybe. F of x equals 1 over x looks like this here. And it doesn't curve back. It looks like this here. And the reason it looks like that is because as I get very close, well, I'm going to show you a table in a minute, but the reason that it looks like that, okay, is because if well, first of all, what can x not be? 0. X can't be equal to 0. And if I plug in numbers very close to 0, like 1 over, if I come from the right side, if I plug in, what's 1 over 0.1? What do I get out? 10, right? So if I get very close here, I get 10. If I go 1 over 0.01, what do I get? 100. If I go 1 over 0.001, I get 1,000, okay? And so this number gets bigger and bigger and bigger as you get closer and closer to 0. And that's when you have an asymptote, when it's you have a vertical asymptote as you get very close to a number but don't touch it. And another way to describe what I just did here is using this notation. The limit of f of x as x gets close to 0 from the right side is equal to infinity. They're going to have a different, we use this in chapter 11, and this is the more mathematical way to describe what's happening. But this little plus sign here, it doesn't mean positive 0. It means I'm approaching 0 from the right side. Okay, see that? As I approach 0 from the right, y goes up to infinity. What would be the limit? Okay, so using the same idea, what would be the limit of f of x as x goes to 0 from the left side?
Y negative.
Negative infinity. Do you understand that? Okay? This is equal to negative infinity. In other words, as I get closer and closer to 0, this function gets closer and closer to a very big negative number. Because if I were to plug in like 1 over negative 0.00001, right? I'd get negative 1, 0, 0, 0, 0, I don't know, another 0?
Yeah.
One more 0. How many zeros? Something like that, okay? I get negative 10,000, which is a very big negative number, and the closer I get to 0, the closer I get. That's why you have asymptotes there, okay? So in the book, they have this little table. This means the same thing. This is what I just did right here. But right now, the way they describe this, okay, I'm gonna skip over this slide. I'm gonna show you this, okay? This is what the way they write it in the book. I gotta put a little dot here to make sure it records. But this says f of x approaches negative infinity as x goes to 0 from the left side, right? F of x decreases without, that's how you say it in words, okay? So as I approach this, as I approach 0 from the left side, I get very, very close to, I get some very big negative number. As f of x goes to infinity from the right side, I get very close to some positive number. Also, is that good? Can I move on?
Is the closest it gets to the origin 1, 1?
Is the closest it gets to the origin 1, 1?
Yeah.
Right here?
Yeah. Is that 1, 1?
Oh, that's a really good question. That's a calculus question. Okay? And you'll do that when you get to it. But you would find that using calculus. I mean, you would. You could do that
Well,
using calculus.
if you put 1 in for x, y equals 1, so wouldn't it just be a point?
It would be, yeah, but is that the closest, right?
Yeah, it would.
Is that the closest it ever gets? I don't know, but you can use calculus to show that it's the closest. I think it is, but you can use calculus to show which is the closest. That's a good question. Okay? Horizontal asymptotes, okay? Horizontal asymptotes occur as x gets as x gets very large in the negative direction or in the positive direction. So going back to our function over here, if I were to draw this little graph, which looks like this, okay? Looks like this on this end, and this on this end, okay? A horizontal asymptote, another way to write what they have here is the limit of f of x as x goes to infinity is equal to 0. That's what this says right here. F of x goes to 0 as x gets very, very big. So as this number becomes very, very big, I get very, very close to 0. As this number gets very, very negative, as x goes to negative infinity, not small, but very big in the negative direction, this also goes to 0. Because if I take a very big number and put it in there, what kind of number am I going to have?
Small.
A very small number, okay? So, right, 1 over, so if I go out here a million places, 1 over a million, how many zeros in a million? 1, 2, 3. 1 over a million is a number that's very, very close to 0. So that's another way of writing what they have down here, which is f of x approaches 0 as x increases. Okay? You got that? Maybe you don't have it, but we're going to get some practice. Okay? So, so you could write this down if you want. Do you want to write that down?
No. Probably not.
Who wants to write that down? Go ahead. Do you need to? I don't think it's 100%. It might be helpful. Okay? The line x equals a is a vertical asymptote of the graph if f of x of f when the y goes to infinity or y goes to negative infinity. So that says that if the function goes to in positive infinity or negative infinity, then x equals a is a vertical asymptote. The line y equals b is a horizontal asymptote when f of x goes to b, or y goes to b, as x gets very big or x gets very small. Okay, that's kind of what that says in words. Okay, I got to pause here for station identity. Whoops, what did I do? Pause, unpause. Okay, so so okay, hush, 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 hush. As I mentioned before, or maybe I didn't mention this, these things are called hyperbolas. Oh, is that how you say that? Hyperbolas. Yeah. What?
It's a new form of Ebola.
Oh, in Italy, yeah, in Italy, after they have the follow-up to the Super Bowl, it's called the hyperbola. You know, so they have the Super Bowl, then they have the hyperbola. You know, because it's a bug. Anyway, no, but a hyperbola looks like this. Okay. It's not bad, not bad. So, horizontal asymptote, vertical asymptote. Here in this rational function, you have a horizontal asymptote as y equals 2, so they don't always have to be at 0 and 0. This one has a horizontal asymptote at y equals 2 and a vertical asymptote at x equals negative 1.
Why is
So,
that 2?
why is this 2? We're going to talk about that in a second. Okay? So, and how you find those. That's what we're going to talk about next, which is the fun part. Okay? So, this is, so I don't want you to write this whole thing down, because this is the thing that I said tomorrow. I'm going to give you a sheet that kind of goes through this in a little more plain English. But these are the rules of how you find asymptotes, okay? So this is, this is a rational function, and this is a rational function. The rational function is just this is a polynomial function, and this is a polynomial function. So it's one polynomial divided by another polynomial. To find vertical asymptotes, okay? The vertical asymptotes are the zeros of the denominator, okay? So you set the bottom equal to 0, and if they do not cancel out, if they don't have any common factors with something from the top, then that's where you have vertical asymptotes, okay? So this is, I'm going to go through some examples of each one, so you'll figure out what they're talking about, okay? No common factors, but basically to find vertical asymptotes, we set the bottom equal to 0, and if it doesn't, if that 0 doesn't cancel out with a 0 at the top, then you have a vertical asymptote. To find horizontal asymptotes, there are 3 rules, okay? And you have to compare the degree of the top equation or the top polynomial with the bottom polynomial. So degree, so say if this number up here were like I started with a with 5x to the 6th plus 3x squared. Okay, plus 7x up top. And over here I have 4x cubed minus 2x. What's the degree of this polynomial? 6. And the degree of this is 3, right? Okay, so it's based on your highest degree term. Okay, so here's your 3 rules. Okay? If the degree of for finding horizontal asymptotes, if the degree of the top, and I'm going to put this on a sheet, I have it already printed, but I'm not going to give it to you right now. But if the degree of the top is smaller than the degree of the bottom, then y equals 0 is a horizontal asymptote. For example, if I have something like y equals 3x squared minus 2x over x cubed plus 5, this would have a horizontal asymptote at y equals 0. And another way to talk about that is like bottom heavy, okay? Because the bottom, as x gets really, 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 really big, this is the y, for those of you who want to know why this is, okay? As x gets really, really, really big, if I take like 1 million and raise it to the 3rd power, and I take 1 million and square it and multiply it by 3, which number is going to be bigger? The cubed one, right? So this one, if this degree is higher than this ends, no matter what I multiply this by, eventually this bottom is going to outweigh the top. And so this fraction will eventually get very, very close to 0, okay? So if it's bottom heavy, you have an asymptote at y equals 0, okay? Eventually this thing is going to go towards 0, okay? This thing says if the second rule said if n equals m, in other words, if the degree of the top is equal to the degree of the bottom, you take the coefficients of the highest degree term. For example, y equals 6x squared, no, 6x, let's do something more interesting. 6x to the third minus 2x squared plus 5. And on the bottom I have negative 2x cubed plus 8. Since the degree of the top is equal to the degree of the bottom, this is eventually, if x gets big enough, all I have to do is compare these two coefficients of the highest degree terms. This is going to approach y equals negative 3 is going to be my horizontal asymptote. Because what happens is if I cube something, this, as these numbers get really, really, really big, they outweigh these things over here. So these things kind of go away. Say, oh, x cubed is much bigger than x squared. So those kind of go away. And these kind of go away. And I'm left with the ratio of this to this, which is negative 3. Yeah?
Yeah,
Okay.
that makes sense.
And then the last thing says if it's top heavy, okay, meaning, okay, this last thing, how do I get, where did it go, okay? So this last thing, I'm just going to grab it, okay? So this last thing says if it's top heavy, okay? In other words, if I have something where the degree of the top is bigger than the degree of the bottom, like y equals 3x to the 5th minus 4x squared. Doesn't matter what's down here. 500x to the 4th minus 2. Okay? Eventually, this top is going to outweigh this bottom. And then I have no horizontal asymptote. In this case, we'll have a slant asymptote, but we'll talk about that tomorrow. Okay? So those are your 3 rules. So now we're going to get some practice. Ready to get some practice? Okay. So find all asymptotes of the graph of each rational function. I'm going to do this one with you, and then we're going to do the next one. This means you're supposed to respond. Okay? Well, who can tell me what is the horizontal asymptote? Horizontal.
0.
Hey, raise your hand.
0.
Right, Nico? 0. Why? That's right. Why is it 0, Nico?
Because the bottom will eventually outweigh.
Yeah, the bottom outweighs the top, right? So if I were graphing this, so eventually, or tonight and tomorrow, really you're going to focus on the graph. I know that this is going to be a horizontal asymptote. I also know that if I plug in 0 in here, what do I get out? 0, 0. I also know that it goes through the point 0, 0. So this graph is kind of weird because it goes through 0, 0. It doesn't look like one of your traditional hyperbolas. This graph looks, I think, more, it kind of does this kind of thing, and this kind of thing, and then it comes over here, and it flattens out close to 0. Okay? So it has an asymptote at 0, but it's kind of like a flat, it flattens out when you go this way. Is there a vertical asymptote? Oh.
Yeah. How do you find it?
You set the bottom equal to 0. So if I go 3x squared plus 1 equals 0, 3x squared equals negative 1, x squared equals negative 1/3. Can I take the square root of negative 1/3? Case? Can I take the square root of negative 1/3? What do I get? No, you're. Can I do this? Take x equals plus or minus the square root of negative 1/3? Can I take a square root negative?
No.
Only if you use i's, and you can't really have imaginary asymptotes. So there are none, okay? There's no vertical asymptotes.
So if it has an I, or if it's a negative, where it doesn't have
Yeah, you can't take the square root of a, I mean, you can't have imaginary asymptotes. Okay? So, now, we did this already. So, find all you guys try this one, okay? Find all asymptotes of this function. Now, I'm going to do this one. Never mind. Change my mind. So, who can tell me the horizontal asymptote?
2.
Why is it 2? Sean?
Coefficients. The degrees.
Because I look at the degree of this, the coefficient or the exponent is the same in both of them, so it's 2 to 1, right? So horizontal, y equals 2 is the horizontal asymptote. How about the vertical asymptote?
1.
No? Ah, very good, Chloe. How did you get that? You're right. You just guessed. Really, what you need to do is factor the bottom. Okay? What does that factor to? X plus 1 and x minus 1. Okay? And then I set this part equal to 0. Well, x equals negative 1 and what? I don't need a parenthesis there. X equals negative 1 or x equals positive 1. Those are two asymptotes. So if I were to graph this function, okay, it has a horizontal asymptote. I'm going to change colors. I'm going to make it dotted. I'm going to make it red. You have a horizontal asymptote going across here at where'd that go? Oh, there it is. Okay, go away. At this is at y equals 2. I have vertical asymptotes, okay, at positive 1 and negative 1. Okay, so here's positive 1 and negative 1. This line down here, don't worry about that little fuzzy thing down there. And then it also goes through the point 0, comma 0. Would you agree with me there? If I plug in 0 in here, do I get out 0?
Yeah.
Okay, so this one, I know it goes through 0, 0. I also know that if I plugged in 3, you have to do, like when you're graphing these, you have to plug in some number. If I plug in 3, I get out a bigger number than 2. So I get a number somewhere over here. So I know on this side, since these are asymptotes, this kind of looks like this. Okay? And on this side, if I plug in negative 3, I get out a number bigger than 2 as well. And over here, since this looks like a kind of a turning point right there, this graph looks like this. It's kind of a funky rational function. How do I know how to do that? I've done that for a long time, but basically you find your asymptotes, you find some key points, and then you could kind of sketch the rest of the graph. You're going to have to do stuff like that, okay? So like if I plug in 3, I get out a number bigger than 2, so I know I'm on this side of the graph, okay? Okay, now it's your turn to try, okay? You try. Oh, that's that last graph that I showed you. We did this one already. Sorry. Boom, 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 boom. Hey, look, I got it right. Okay, so, oh, I haven't talked about this yet either. Okay? So, holes in the graph, okay? A hole. A hole occurs, okay, at the value that makes the value, at the value that makes the hole occurs at the value that makes the value, what? That makes the function undefined, okay, if something cancels out. So, can you guys tell me how to factor this? What?
X less than 2 minus 1.
X minus 1. So here's where you got to practice your factoring. On the bottom, x minus 3 times x plus 2. What happens with those x plus 2s? They cancel out. So I have a hole, okay? I have a hole at the thing that cancels out, okay? At -2 comma something, okay, not 0. You have to figure out what that other thing that goes in there, and everyone always gets this wrong on a test, so you should learn it right now. This is how you do it, okay? A whole at -2 something. Anyone know what that something is?
Don't you plug it back into the equation?
If I plug it back into the equation, I get 0 over 0, which doesn't tell me anything. So what I have to do is plug it into here, okay? Plug in -2 into here, because what this says, so this function, x minus 1 over x minus 3, looks exactly like this function, except at 2, I have a hole, okay? 2 what? Well, if I plug in 2 in here, I get -3 over -5. So at 2 comma 3/5, I have a hole. So let me just, I want to grab this and put it on a new page so I can sketch this graph. So if I have this right here, okay, and I'm trying to graph this rational function, uh-oh, my lines are dotted. That's okay. I have a hole at -2 comma 3/5, and I put a hole in the graph right there. I also know that I have a vertical asymptote where? This one doesn't cancel out, okay? So if this doesn't cancel out, then I have a vertical asymptote at x equals 3. So different color, green, different dots here. At x equals 3, I have a vertical asymptote. X equals 3. And then what's my horizontal asymptote? Look at the original equation.
1.
y equals 1 is correct because the ratio of these two is 1 to 1. So then I have a horizontal asymptote at y equals 1. Got it? Oh. Y equals 1. Whoops. The hole should be below that, right? Hole is below that. Oh, crap. Oh well. Here's the hole, right about here. Okay? Let's connect those two things. There. Asymptote. Okay? So if I were to sketch this function, I gotta look over here or I'll mess up. It kind of looks like this. It goes this way over here. It kind of goes through that hole, but it doesn't touch the hole. And then it comes over here to this vertical asymptote. And then over here, it does this. Okay? So it shouldn't touch the horizontal asymptote. But it goes like this here, and there's a hole right there. Okay? So this graph looks exactly like the graph of y equals x minus 1 over x minus 3, except I have a hole. It's the same graph, except there's a hole at that point. So this one, the only difference between this and this is that there's a hole right there in the graph. And if you plug into your calculator this thing, it won't. Most calculators won't show you the hole, but if you look at the table, you'll get undefined right at that point. It's weird. What's weird? It's just weird, man. Okay. So now finally, you guys tell me this. Valuable participation point, or bonus point. Go ahead and give me that answer. Okay? No, we're looking for the coordinates. This will take you a minute. Okay? Coordinates of the hole in the graph. Go ahead, Laura. What do you factor the top two? X minus 2 and x plus 1. Okay.
2x plus 1 and x plus 1.
Very good. And then what?
X coordinate is -1.
These cancel out, right? So you have x equals -1, and then,
You plug it into the other two.
right, you take that, you don't plug it into here because you're going to get 0 over 0. So you take that, you plug it in here, and you get what?
-3 over -1.
Very good, which is equal to 3. Okay? So you have a hole at -1 comma 3. Your answer isn't complete until you say the x and the y coordinates of the whole.
Can I
Okay?
get a lollipop for that?
Why should you get a lollipop?
Because I helped out.
Okay. Here you could tell me the answer. This is the same equation. Okay. Find the vertical asymptote. So going back. Whoops. Going back. Who can tell me the vertical asymptote? Raise your hand. Sean.
Negative 1/2 and negative 1.
No, not negative one.
So
Negative one is a whole.
Oh, just kidding. It's like, no, it can't be negative 1 because it's a whole. So.
X equals negative 1/2. So it can't be both a whole and an asymptote. So you have an asymptote at x equals negative 1/2 because that's the thing that doesn't cancel out and makes the denominator 0. Who can tell me the horizontal asymptote?
Yeah, it's 1/2.
1/2.
Raise your hands.
Oh, me. My hand was up first.
No, it was
My
like
hand was
Hannah.
up.
1/2. Y equals 1/2. Okay? So, you want a pointer or Tootsie Pop? Yeah.
Well,
Yeah.
Anna said I could have
I'm giving you a point.
Oh, I get a point?
Yeah.
Okay.
Wait, who answered back there? Sean, you want a Tootsie Pop
Sean
or a
messed it
point?
up though.
I'll take a point. Sean does.
No, he doesn't get a
Oh, I
point.
get my
You got it
point.
wrong.
I can use the point.
Okay, so I think after that, we can do that. I just want to show you this. So there are some real life applications of this stuff, okay? If you, so this is a rational function where this is the proportion or the percent of pollutants in a smokestack, and this is how much it costs to remove a certain percentage. Okay, so if they remove 85%, I plug in 85 in here, and that'll give me how much it costs to remove the pollutant. If I want to know how much it costs to remove 90%, I plug in 90 in here. Notice that this cost goes up very, very quickly. Because can I remove 100% of all the pollutants in the smokestack or something?
No.
It's kind of like I talked about, we just had our house tested for radon, and stuff. You can't get rid of every single, radioactive particle, but you can get rid of most of it, right? So a lot of times those follow this kind of relationship. And going through really quick, you would just plug in those two numbers. And there's a difference of cost of $266,000. Things go up very, very fast with rational functions. Your homework, yay!
That's too many. I can't count.
This isn't your homework, it's on Schoology. So this from last year, okay?
Can you shorten it?
Shorten it, no. Oh! But some of you guys, hopefully by tomorrow,